So I know I'm the last speaker before we all get to relax and have a couple of drinks. I will try and keep it brief, at least not go over. This is the devil in the details, Kubernetes first security assessment. My name is Aaron Small. By day, I'm a product manager at Google. I work on Kubernetes security and GKE. With me, I've got Jay Beale. He's the CTO of InGuardians. They do a bunch of Kubernetes penetration testing, and he's also a seasoned instructor at Black Hat, so we're really lucky to have him both with us today and also for all of his contributions on the audit, which is what we're going to talk about.
So these are the other two co-leads for the working group. These are the guys who are smart enough to avoid having a slide deadline. Craig Ingram works for Salesforce, where he works on securing Kubernetes, container, and cloud for Heroku. Joel Smith of Red Hat works on OpenShift, and he's also a member of the Product Security Committee, and we'll talk about them both a little bit more. You're going to notice that there are little logos next to our names. Aaron and I both have our open source projects. You can get a sticker for one of mine if you catch me afterwards. Craig's is for his Capture the Flag team, and Joel's was pretty cool, is for his Project Euler level badge. So if you're into math, take a look at that.
Okay, so we have like 30 minutes to talk about a security audit that took us a year to plan and execute and yielded 241 pages of white papers and reports. We won't be able to cover everything, so instead I want to give like kind of an overview of the Kubernetes ecosystem that surrounded the audit, why now was the right time to run it and to invest all this time and money and energy into it. We'll also talk about the philosophy that grounded our approach to it and why that's a little bit unique with Kubernetes. And we'll look at Kubernetes through the lens of an adversary and how that can help shape our thinking.
And then we'll talk to you about the high-level results of the threat model and of the source assessment. We'll talk about next steps, and then in true open source fashion, we'll ask you for help.
Okay, backstory. This whole journey started back in 2018. The CNCF reached out to a couple of their projects. It was InGuardians, Prometheus, and Envoy, and asked them to run a security audit. It was kind of a trial balloon to see if a formal audit process like this would bring value. The short end to that long story is that it did. They got good findings, they got good bugs, and overall it improved the security of those products. At the end, we'll have links to those initial reviews if you want to take a look at them. So we left at the opportunity when they opened it up to graduated products. And the steering committee said to the community who would be some good people to run an audit like this, and we formed the working group. It's gone through a few iterations since then, but by and large, the people you just saw up there have been working on this for just over a year. So I said, why now? Why is this the time to invest in an audit like this? I think it's important to acknowledge that Kubernetes has become business critical. It's the de facto way to run containerized workloads, and containerized workloads aren't just for our side projects anymore. The world runs on them. This is a survey that the New Stack ran back in 2017, and even at first glance, it's apparent that Kubernetes was like far and away the leader, but then we dug in a little bit. It turns out it's actually check all that apply, so many of the other responses were probably also running Kubernetes. And if you dig in even deeper, you'll notice that a bunch of the options are just Kubernetes under the hood. Also, security is top of mind. Is the #1 challenge reported for people trying to adopt containers and the containerization methodologies. And it's an entirely different security model than these more traditional companies were accustomed to. And while this survey was taken back in 2017, it's not like interest has been declining. I know Google Trends is not the most scientific approach for interest, but I think it tells a pretty clean story. It's about a 4-fold increase since 2017 when that survey was taken. Also, this is Kubernetes time in the spotlight. Not only is it business critical to those people who have adopted it, but it's being very widely adopted. And it's being adopted both in cloud native companies, but also more traditional ones. Some of those companies operate in very security sensitive industries. We have banks, we have financial institutions, we have e-commerce, we have retail. We even have CERN. So like, don't let CERN get hacked. Finally, this isn't theoretical. The vulnerabilities exist, and they're being exploited in the wild. I know a couple people in this room work on managing and reporting those vulnerabilities every day. It's very real. Eye charts and headlines aside, what this means to me is that our market is calling out for maturity, and security maturity at that. One of the ways that we can demonstrate this maturity is to run these independent third-party audits. In the more traditional software acquisition model, these would be part of the package that a company would get when they were looking to adopt a new piece of software or a new software stack. The open source nature of Kubernetes does change this a little bit, but that need to demonstrate maturity remains. So when we approached this audit, a number of us had done this before. I've run lots of audits. Other people on the team had run audits. But this was different than anything any of us had done, and that's basically for two reasons. Kubernetes is very, very, very big, and it's open source. So instead of trying to run our old playbooks, we decided to build some fundamental philosophy around how we wanted to approach it. First, Kubernetes is built in the open, and we wanted to audit Kubernetes the Kubernetes way. So to this end, the RFP that we published to get proposals from potential vendors was all written and published in the open. I think more interesting than that, though, the selection methodology for how we picked each vendor and what the criteria was for selection was also all published in the open. I want a big thank you to Craig Ingram, who wrote our publication around why we picked who and what the criteria was. And we're doing this because we hope that by keeping the framework open, it enables repeatability. Not only repeatability for subsequent open source Kubernetes audits, but any open source project can take a look at our methodology and either just use it or they can improve upon it. We also opted for as much transparency as possible. Of course, when you're handling really sensitive information like undisclosed, unreported, unpatched vulnerabilities in something as big as Kubernetes, you can't be very carefree about it. So we did follow industry best practices. It turns out that attackers are notoriously faster at building exploits than defenders are at rolling out patches. So we gave the Product Security Council time to review all of our findings and potentially embargo them before we published all of them. But we did eventually publish all of the findings and also all of the qualitative analysis of Kubernetes. Also, in the vein of transparency, the vendors who were working on it, the security vendors, they did all of their work and all of their research in their own private GitHub repo. And then when we finished, after we published all the findings, after we published the white papers, they actually opened that repo up to the world. So you can read there, you can read all their scripts, you can read all of their incomplete findings, all the dead ends, and all of their, let's call them enthusiastic debates about whether something was a vulnerability or not. That link's at the end. I'd highly recommend you go dig in. Frugal, all right, we were working with the CNCF. The CNCF is a nonprofit. We wanted to be good custodians of their resources. One of the ways that we did this was we tried to focus our efforts on what we thought were the most security critical components of Kubernetes. We didn't want to peanut butter our efforts over the 1.4 million lines of code that is Kubernetes. So we just picked the key areas to get to some level of depth. In the areas that we did look at, we didn't want to leave anything on the table that was obvious. We wanted to have some level of confidence we had found what was there. Finally, we wanted to be future focused. To this end, we knew we couldn't cover everything, and we knew this couldn't be the last audit. So we wanted to invest some of our resources into creating a threat model and an attacker's guide. We want this effort to pave the way for future research, both by independent researchers and more formal processes. So from that philosophy, we asked for these 4 deliverables. I know it's a very pretty slide. Thank you. These 4 core deliverables from the researchers. We wanted the traditional assessment, which is a list of vulnerabilities. We wanted to give the researchers time to go find these good vulnerabilities, learn how to exploit them, and report them back to the PSC. But we also wanted to create some documents to help future research. And these were the attacker's guide, which it covers how to build a reference cluster that's good for attacking. It'll tell you what the networking layer might look like in that cluster. And it discusses what the available attack surface is on all of the critical components. The threat model, of course, we talk about data flow between these components, what the trust relationships are between them, as well as a body of qualitative findings that I think are really useful for attackers and defenders. And then there's the operator white paper. The operator white paper is effectively what you need to know about defense from an attacker's perspective. If you have Kubernetes in your job description anywhere, I think this should be required reading. Okay, that's my initial spiel. We're going to move into what the attacker's perspective is, and because Jay is a professional Kubernetes attacker, he's going to take over.
Cool. Thanks, Aaron. So let's see. So when we're exploring or exploiting a cluster, we're thinking, here's how we're thinking about it. We're thinking about how data flows through the cluster, both in the control plane and even through the workloads. We're targeting critical components, especially anything that could grant us access or do something that developers or operators didn't intend or hopefully didn't even think of. We're watching to see whether network isolation is either hampering us or more often restricting our view of the situation of the cluster. We're looking to evade that isolation or otherwise try to break it. So part of how we do that, we'll look at how we can traverse trust boundaries and how we can gain lateral levels of privilege that might give us better visibility around that network isolation. We'll be looking at how we can escalate privilege. We're trying to find any opportunity to perform a monkey-in-the-middle attack. I demoed one of these in a recent talk, actually, where I was showing if an attacker can create pods in a namespace, then they can basically monkey in the middle any traffic that's headed to a service in that namespace. Let's see. And perhaps most crucially, we're trying to get or modify secrets. And those could be access tokens. They could also be passwords, TLS private keys, configuration lines, anything the defenders don't want us to get at. So the other interesting thing from an attacker's perspective is to think about the vantage point at which you're attacking a cluster. So on first glance, people tend to think about attacking something, meaning that you're hitting it across the internet. As an attacker, we consider those situations to be lucky breaks, those places like where Tesla happened to leave their dashboard available to the internet, basically unauthenticated, as I recall. That happens, but it's kind of rare. So as an attacker, most often, we're attacking Kubernetes clusters from inside the cluster. So how do we get inside the cluster? Most of the time, we're working from some compromised workload on the cluster. If we're really lucky, that's some control plane element. If we're really, really lucky either way, there just happens to be a container breakout vulnerability that gets us execution on the node. We're going to look at this a little more graphically on the next slide. And this is the one time where I get to use my laser pointer. Aaron, can you just put your eyeballs right? No. We've had to argue here and there about content, so give me the laser. So this diagram actually came right out of the threat model, and it's pretty useful. So as an attacker, like the first place is I might be coming from outside the cluster, and you'll note it says user here and it says external attacker here, and for me those are the same thing. I'm a security guy, so when I'm a defender, I think every user's an attacker, and when I'm an attacker, I'm an attacker, so of course I think everybody's an attacker. So anyway, I can be, when I'm coming from the outside the cluster, I don't see a lot of attack surface. I see any of the ingresses, any of the services that actually land, any of the services that are exposed outside that land on pods. And that's, what am I saying? I'm sorry. So I've got, so that's, that's what I'm seeing from outside. And I need that, and that's my main way of actually getting into the cluster, is basically, can I find a vulnerable workload? I have an intentionally vulnerable cluster called Bust-a-Kube. That's what one of my stickers is for. And in this Bust-a-Kube, every capture the flag scenario in it starts with a vulnerability in one of these pods, so that you have an excuse for being inside the cluster. But before I get there, what else do I see from the outside? Often, I don't see much, right? I see services that land on pods. If I'm lucky, I might have one of those great situations where I'm attacking something in the cloud and the installer has set up the API server so that it's available to the entire internet. That kind of mistake is rare, but I might find it. Finding any other control plane component that's accessible from the internet at large, good luck. So I don't see a whole lot from the outside. Now when I'm inside, I have far more attack surface, and that's what this whole right side of the diagram is. First, I've got every pod in service, not just the ones that have ingresses from outside. I might have access to attack kube proxy. Then next I've got the API server, and the API server is where I do most of my attack work on a pen test, or from a bad actor where I do most of my work to try to get access and get my whatever I'm going to do with this cluster, cryptocurrency, data theft, or what have you. So I can almost always see the API server. In fact, since most clusters don't have egress network policies, I can often also communicate with the kubelet on each of the pods. So I'm almost always able to see the cloud provider APIs, and honestly, that's where like half of the juice comes from, including this metadata API that'll give me cloud credentials that let me interact with all the cloud APIs. And honestly, a bunch of cluster compromises come that way. But I'm on a tangent. So even in an on-prem cluster, I'm still looking, even in an on-prem cluster, there's still going to end up being some kind of data center resources, often data center APIs that are providing the cluster with storage, but sometimes just whatever the heck else was in that data center. Let's see, what else? So attacking the scheduler and the controllers is available, but to be honest, most of my access to those is coming through API server before I can get to those to the other master components. etcd again is also similarly something I basically attack starting from the API server. So finally, I might be able to attack the container runtime when it and when I get lucky there, I really like it. The biggest place I end up getting an ability to attack the container runtime if I don't have some kind of way of breaking out of the container is if I end up in a wonderful container or a wonderful pod that has the Docker socket or what have you mounted in. And before you think that's unrealistic, it's not. Talk to me after. So, okay. So Aaron actually convinced us in the working group to put threat modeling on this effort that was looking for bugs and vulnerabilities. Aaron spoke very strongly about the need to get threat modeling and convinced us. So I want to let him talk about that.
Can I have the beeper?
Yeah.
I felt so strongly about this because I kept talking to independent researchers in the security community, and they kept telling me they wanted to hack on Kubernetes, but they didn't really know where to get started. I wanted to unlock all of that talent that exists out there, and one of the ways I could think of to do that was to hand them a threat model or like a roadmap for how to attack Kubernetes. A good threat model really highlights where the critical security boundaries are and what assumptions the security model is grounded in. I've been threat modeling software for most of my career, and the methodologies I've developed over that time tend to result in like really detailed, really deep threat models. For those of you who are in the biz, it's like the Atom Showstack model that Microsoft adopted. But I was working with this guy, Stefan, from Trail of Bits, and we elected to take a different approach due to the unique nature of Kubernetes and the unique distributed nature of all the talent that built it. We went for a derivative of Mozilla's rapid risk assessment model, and primarily we chose that because the people who know where the bodies are buried in Kubernetes are scattered everywhere. And they might not necessarily have a security background or know exactly how to talk about the security controls that they built into their software. So we needed to unlock that knowledge. We need to view it through a security lens, and then we need to draw conclusions from it. The rapid risk assessment is just really good at getting people who aren't security people to talk about security stuff. So in the end, we used that process and we interviewed a bunch of people across a bunch of different SIGs and distilled that into a consumable report. Jay's going to talk about some of the stuff we found.
Cool. Thanks. So the most common question we've gotten when we talk to people about the threat model is, why these components and not others? Well, the question really should be, why these trust zones? And some of you are probably thinking to yourself, well, wait, what's a trust zone? So we looked at the architecture of a Kubernetes cluster and broke it down into these 6 areas. So components in these areas, and I really should be using our pointer, I guess. Components in these areas have very few security controls between them. So trust zones, areas. So components in these areas have very few security controls between them within the area, but each of them are responsible for enforcing controls on communication that are passing into and out of their area or trust zone. So for example, the API server can't blindly trust the internet, but the worker components implicitly trust the API server. And the API server, in turn, fully trusts etcd for its state of the world, for its view of the world. So we looked at each of these trust zones and chose the components in them that had the biggest security impact on that zone. So at the top of the food chain, you have etcd and the API server. And now these are the crown jewels of the cluster. If you're able to control these components, you have full control over the cluster itself, and it's just game over easy. In the controller manager zone, we looked at kubescheduler, kubecontroller manager, and the cloud controller manager. And these components control the topology of the cluster. And if you own them, boom, privilege escalation. So a lot of the Kubernetes security controls also are actually really node-centric. For example, Kubernetes will make sure that the secrets secrets are available only to the nodes that have pods scheduled on them that actually need those secrets. Well, if you have any control of scheduling, then you can trivially bypass that control and make sure that the node that you've got compromise on has the secrets you want. We looked at the kubelet, which ties Kubernetes to the container runtime, and to kubeproxy, which handles the pod's networking needs. If you own the kubelet, you own every workload, secret, data volume on the node. If you don't, but you own kubeproxy, you get to control where all the network traffic goes that's on its way to or from pods. We didn't look at any specific container runtimes. Instead, we looked at the container runtime interface. We had to make sure there weren't any bad behaviors introduced by the container runtime interface's abstraction layer between the kubelet and the container runtime. So next we're going to talk a little bit about the threat model's results. So we're giving you the highlights. As Aaron said, this effort produced hundreds of pages of really, really useful stuff. And we have 35 minutes, so we're going to give you the highlights. So first, there are at least a couple areas where a user can configure a security control, have the API server accept that security control, and then have that configuration achieve no result. We'll call that a no-op. So as an example, if you're using a networking provider that doesn't support egress policies, you can put egress rules in place, but Kubernetes won't warn you that you haven't actually got any firewall rules governing outbound traffic now. You find out only if you either do your own test, or if you're like most people, you find out when an attacker shows you that there was no egress policy enforced. And they show you in a really bad way. So pod security policies have the same problem. You can apply a policy, but if you don't realize that you have to actually activate the pod security policy admission controller, you're left thinking that you have policy enforcement when you don't. And that's kind of, that's another case where you think you have a control, you don't have it. It's kind of fail silently, or apparently sail violently. So second, the threat model pointed out that we're not perfect or even consistent on how we're using transport encryption. They found some use of clear text HTTP. They found that some of our HTTPS doesn't check the server certificate, making us open for monkey in the middle. Unfortunately, the one thing we are doing consistently is setting Kubernetes internal SSH connections to never check the server certs. Let's see. Third, the threat model found out that we weren't doing enough to stop a worker node compromise from leading to a cluster compromise. We're going to speak to this a little bit more in a couple slides. Fourth, researchers told us that we really needed to provide a unified audit trail so that you could trace an attacker's path through the system. You can do this in Kubernetes, but it's not a default configuration, and this is something that every incident responder needs to handle a breach. You have to be able to lay down that timetable, that timeline of what happened. Fifth, and probably the toughest to solve here, is that the controllers all have the same level of privilege due to their being compiled into one of two large binaries, either the controller manager or the cloud controller manager. So the researchers recommended that we figure out how to do least privilege here. In addition, I'm going to move on and talk about the source assessment findings, but you should know that in addition to the final threat model report, which has more than I'm just giving you in these highlights, all the raw rapid risk assessment docs are available in our repo if you want to dig a little deeper. So now I'm going to talk about the source assessment. In this 2019 round, we had to split the time between a bunch of deliverables. We've still got a heavy focus on bug hunting. They found 37 vulnerabilities, which got reported in through the Product Security Committee, the PSC. So Craig opened an issue for each. Joel coordinated with the PSC and what actions we could take in it, like embargoes and so on. On the next slide, we've got a chart with some of the highlights. So the first one is those non-authenticated HTTPS connections, which we've already talked about. In the second one, we got dinged on not supporting certificate revocation. This is another one that's really important when you have a breach. If the certificates can't be revoked and the attacker got those certs, then the attacker might have access a lot longer than you think they do. In the third finding here, we've got a pod security policy bypass, and this one was kind of fun to me because if you've ever mounted the node's root file system into a container, and that container is running as root, this is something we do in Docker all the time, we're just playing with Docker, not Kubernetes, you realize it gives the attacker a great opportunity to compromise the node through its file system. So the canonical way to prevent pods from doing this is with pod security policies. And the source assessment team found that an attacker can get around this restriction just by mounting the node's file system as persistent volumes instead of as host path volumes. Fourth one was a time of check, time of use vulnerability. An attacker could chain with another one to get privilege escalation for their container on a node and get full privilege on the node. The fifth one was pretty cool. Researchers found a directory traversal issue in kube-control copy, and because it uses tar. And here's what was cool. The vulnerability had already been discovered and fixed by the Kubernetes project, but the fix had a bug. So the work was valuable. In the last one, we combined a couple issues that concern turning a node compromise into a cluster compromise. And this is kind of this is a medium, but it's still really, really worth highlighting because it points to something systemic. One was bearer tokens being logged to the node's system logs. The other was the iSCSI credentials, whenever using iSCSI for volume storage, being logged to the node system logs. And these point to something systemic, not just with logging, but overall, Kubernetes isn't particularly hardened against an attacker who's able to break out of a container and take administrative control of a node. Once you're on a node, there are privilege escalations. Some are obvious, like credentials being visible on the command lines and environment variables being available and having secrets in them. But others are less obvious, like tons of world readable and world writable file permissions. I really like this whole area for research. And there's a talk tomorrow by Greg Castle and Tim Alclair.
He's here somewhere.
Yeah.
There he is.
So Greg's in the back of the room. Afterwards, please mob him. But there's a great talk by Greg and Tim that looks at turning a node compromise into a wider cluster attack. And so we really recommend that. And honestly, I recommend that as an area for research. So I also want to show you a quote from the report's exec summary. And it says we need to do three things. The one is we have to ease security configuration because it's too easy to accidentally configure Kubernetes badly. And that leads to vulnerable clusters. And those vulnerable clusters may not be our fault, but it's our responsibility to fix the situation. We can also improve documentation in the code, both by getting more of it, but also making sure to document our dependencies, especially when we're dealing with external dependencies. And then finally, this is kind of tied to that HTTPS thing. There are tons of places in the code where somebody implements functionality, somebody else has implemented in another place, and it's been implemented by someone else in another place. So you have a ton of this logic implementation. And they said, listen, you've got to find these. You've got to stop having like a whole ton of different places that are starting up HTTPS connections, and just make one library that does it and does it well, and then educate everybody so that they use it. So this being an open source talk, it's time for us to ask you to help and join in. Fixing issues that got CVEs was the urgent and important part on that Eisenhower urgency importance quadrant thing that the Product Security Committee has responsibility for. But that leaves a good bit of systemic work to do. And so here are some things you could do. And I'm just going to touch on a few from this slide. So you could take one of those areas where we have tons of reimplementations and make that central library. You could create a better default audit policy, either for the project or at least for some of the installers or distributions. Find some weak file permissions in the code base and improve them. Here's getting a little bit more focused or systemic here is you could work on documentation for the developers that avoid these issues. You can also focus that documentation on approvers so that the approvers are able to catch more of this stuff on its way into the code base. Finally, you can attack Kubernetes and find vulnerabilities and report them in. And of course, you can participate in the next audit.
Well, go back.
Oh, yeah.
Because I only saw like 3 people take pictures, and this is your homework slide.
Good point.
Yeah, we actually really do need your help. We are getting started on the next round of audits. We'll have ways to get in touch with us at the end, but like we need help now with all this stuff. There's a ton of the qualitative stuff that came out of the reports are like real, and we need to fix them so Kubernetes is more secure and CERN doesn't get hacked.
Okay, phones out right now, or there'll be no drinks.
No drinks. We're going to take just a very brief second to say thank you. Everyone on the working group was really phenomenal. Craig and Joel, who we already mentioned, were so helpful. Chris at the CNCF not only helped us get the money to fund it, but was our liaison with them for anything that we needed. It was incredibly helpful. And everyone who volunteered to work on the threat model, I don't know if we got everybody here, but these people are very busy, and they spent a ton of their time to make this a quality report, and I think it shows some good results.
If we missed anybody there, it's my fault. We'll publicly correct it. We'd also like to thank the first 2 third-party firms to participate in Kubernetes, in third-party Kubernetes audits. That's Trail of Bits and Atredis partners. We want to give special thanks to Stefan Edwards and Bobby Tonic for their great work, and you should catch their talk too. Finally, we'll thank you in advance.
Let's go fast. He's standing there. All right.
Okay, cool. So also there are 5 great attack and defense talks we want to recommend here. The last one on the slide is my recent Scott Pilgrim themed attack and defense talk from Blue Hat a few weeks ago. The others are talks at this conference, so here's your schedule. On Tuesday, you've got Tim Alclair's and Greg's talk on node privilege escalation. Then Wednesday, you've got Trail of Bits talking about their threat modeling work. On Thursday, catch Ian Coldwater's keynote in the morning. And then Brad Giesemann's 90-minute tutorial. And most of the talks here are like 35 minutes. You're getting 90 minutes. That's some good stuff. And that guy really puts a ton of material in his stuff. So
if you've ever seen his talk before, he also talks really fast. So 90 minutes of Brad is going to be something to see. So
it's got to be like 3, 4, 5 hours worth.
Okay, do we have time for questions?
Yeah, we can do a couple.
All right, are you going to run a mic?
I am going to run a mic.
Awesome, thank you.
All right,
I'm going to leave this slide up for questions, though. This is another photo slide. It's all the reports, links to everything we already talked about.
Thank you. Big round of applause. All right, I think we can probably do 2 because we have a short closing we want to do all the way in the back, of course.
Santiago, working the Intoda project. Can you go back to your threat model slide?
Which one? This one or?
The one was a list of 3-layer.
Yeah. This one?
That one.
So I'm curious, did you guys, if at all, considered things such as developer compromise or build system compromise or anything that happened at the left of the deployment?
We talked about it a little bit. Short answer is no. Long answer is we were trying to stay as focused on the Kubernetes as defined by what's in the Kubernetes repo, as opposed to Kubernetes as defined as the thing that runs your application. And the reason for that was just we didn't have time to cover every potential CNI plugin, every potential container runtime, or the entire attack surface that exists before and after the cluster is up and running. I do think that's a fantastic place for research and probably where I would start as a malicious actor.
Right.
But no, we didn't cover it in the threat model.
Yeah, when I talked about how we end up inside the cluster, I left out the idea of the malicious developer or the compromised developer. But that's very realistic, and that's where a lot of tests start, a lot of attacks can start from.
But that developer would then start their malicious action from one of the components modeled, right? So you can at least build the depth defense for that attack while maybe not having the edge covered.
It goes back to what you were saying of if you have a lot of repeated code and obfuscation of that regard, it's very easy to hide a backdoor, right?
Certainly. What the gentleman said was, it goes back to something else you were saying earlier, which was if you have a lot of repeated code, if things are not as commented or not clear, it's a whole lot easier for a compromised developer to insert something bad. And we've all seen that with Linux kernel. I remember the first big Linux kernel privilege escalation was like a double equals sign being changed to a single equals sign meant you got root.
All right, one more.
You mentioned about 240-page white paper on the research that you have done. Where is that? Is it available for download? Or
At the end of this presentation are every link you could ever want. Yeah, so the report link is going to take you to our repo on the Kubernetes repo, and it has all 4 papers and all of the supporting RRAs and everything is up there.
All right.
Hey, thanks, everybody.
Thank you.
Thanks, everybody. Get a sticker.